Good morning or good afternoon, depending on where you are. My name is Professor Orata. We are continuing with our thermodynamics lecture series. Today we want to compute work done in machine cycles. And the machine we are talking about is the reciprocating expander, where we talked of the piston cylinder model. Just let's remind ourselves, we talked about, there's a lecture which we did on compressors and reciprocating expanders. Let's just remind ourselves so that we are not lost. So we want work in machine cycles. So remember, we had our piston and the cylinder. We have our piston and the cylinder. Not very straight. And we said this was our piston. And of course it has some rings. These rings would be oil and compression rings. We had our top dead center. We have our bottom dead center. We have the clearance volume. And here we had our inlet valve, outlet valve, inlet valve, and then we have a rod, this connected to the crankshaft. It's a rod. We have reciprocating motion. And we have here we have the rotary motion. I think basically we have that. Now, when the piston moves up, when you have expansion, we have reduction in the volume. When you have compression, we have on expansion, we have increase in the volume, and compression, we have reduction in the volume. So that if you look at a simple illustration, like the one which was used to derive expression for work for reversible processes, where we just have a piston, and we have the cylinder. So this is the cylinder, that is the piston, and we have gas confined here, and we have external pressure from the atmosphere. When the external pressure is greater than internal pressure, the piston is pushed down. And this change in volume is what we call swept volume. Similarly, when it's greater, pushed up, back and forth. So it's very important to know those terms. The clearance volume is not the swept volume. Clearance volume is not the swept volume. It is a latitude of space which is given so that the piston does not collide with the cylinder head. So it gives that latitude so that the piston does not collide with the cylinder head. But of course, when we are putting in the fluid, and the complementary fluid which is associated with the clearance volume, then it tells you that the clearance volume will affect the capacity of that particular engine. Now, let's go to our work. Let us look at an idealized cycle for this machine cycle. Let's call that state point 1, state point 2, state point 3, state point 4. The cylinder pressure. The cylinder volume. Now I want you to remember when we talked about this reciprocating expanders, which when we talked of it, look at that lecture please, so that you are kept in touch. That lecture on compressors and reciprocating expanders, we had that cycle. So that was 1, 2, 3, 4, 5, 6. That is volume, pressure. Cylinder volume. Cylinder pressure, cylinder volume. And we say that for these state points, I want you to always remember, at state point 1, let's remove this now so that you get some working space. At state point 1, at state point 1, we have the inlet valve open so that you can put in the fluid, and of course you put in the complementary fluid which will go to the clearance volume, and so that tells you that the clearance volume can actually affect the capacity of the engine. Now, at state point 2, we are at the top dead center. At state point 3, we have the inlet valve closed. At state point 4, at state point 3 to 4, we have the adiabatic expansion. Also at that 4, we have the outlet valve open. At state point 5, talking about diagram 5, we have our bottom dead center. And at 6, the outlet valve closes. Just in passing, remember that you have the fluid, pressure, volume. So we have the fluid which when the inlet valve is open, which is put into the system, and also the one for clearance volume, which we are calling delta MC, clearance volume. And this is the fluid put in the system. So if you look at that, what we are saying is that we will have delta MF plus delta MC, and when we are done, this delta MC, which will be compressed back to complete the cycle. So here we have delta MF plus delta MC. Those liquids undergo compression and expansion within the system, and of course it will exit at some point here. MF will exit at some point here, and then of course at this particular point, both valves are closed, so we will have compression of the clearance volume fluid, at that particular point. Now, how do we compute work? For this machine cycle? How do you compute work for this machine cycle? Let me remove this other one so that you don't confuse yourself, but you have remembered what you have talked about in terms of that particular reciprocating expander. Now, how do you get work done? Now, if you go back to our discussions on Carnot cycle, is in one of those lectures, discussions on Carnot cycle, we say that for you to compute work for this particular cycle, you have to integrate over the whole process. So we have to integrate over the whole process. That's a cyclic integral. So we have to integrate over the whole process, and remember dW is P dV. Of course, remember, even if it is this dV here, I want you to always remember I denote A dl. And A is the area or surface area of the piston. And dl is the length traversed for the swept volume. Remember that. Always remember that at the back of your mind. Now, if we write for this cyclic integral, dw, then we will have four line integrals associated with each process. 1 to 2, 2 to 3, 3 to 4, 4 to 1. So we will have 1 to 2, p dv plus integral from 2 to 3, p dv plus integral from 3 to 4, p dv plus integral from 4 to 1, p dv. So those are four line integrals. Now, let us solve them. W. For this particular point, the pressure is constant. Let's call it P1. At this particular point, the pressure is constant. Let's call it P2. That's the cylinder pressure. Remember? We erased it. This is the cylinder pressure. P. Now, the work done, step 1 to 2, is basically P1 times the change in volume V2 minus V1. The work done in step 2 to 3, remember this is a adiabatic expansion, and we are saying that it obeys the polytropic equation. PV, N is equals to a constant. The same with this one here. So this one here and this one here. They obey the polytropic equation. PVN is equals to a constant. We have derived the expressions for polytropic equations. So if you go to our discussions on polytropic processes, you are going to find it there. I encourage you to do that kindly. Now, so because there's a polytropic process, we know that the expression for it is P2V2 minus P1 V1 over 1 minus N. And of course, remember we said that is the polytropic index or expansion compression index. Now, in the next step, we have 3 to 4. Again, that is P2 into V4 minus V3. And the final one, the polytropic process associated with that, will again be P2 V2 minus P1 V1 1 minus N. Now, let us solve these particular expressions now. Let us solve those particular expressions there now. P1, for this process here, there is no work done. This is purely mass transfer. The same with this one. This is no work done. It's again mass transfer. So we are left, so that is 0 and that is 0. These are mass transfers. W0. Mass transfer. W0. So we are left with W is equals to P2, where are we? P2 now, let's put in the values, becomes V3 minus P1 V2, 1 over 1 minus N, plus P2, where are we? V1 minus P1 V4, plugging the values 1 minus N. That's the expression for work there. Now let's work with it. Let's rearrange it so that it looks more organized. So we are saying that W is equals to P2 V3 minus P1 V2 over 1 minus N. And then we have plus P2 V1 minus P1 V1 V4 over 1 minus n. Of course, you can factor out 1 over 1 minus n, then you get P2 minus V3 minus P1 V2 plus P2 V1 minus P1 V4. That will give you the expression for work for this machine cycle. And of course, like you have said, when you're talking of those liquids, remember this cycle, when you're talking of those liquids, that is the liquid which you put in plus the one for the clearance volume. In fact, the profile which you have is like you have delta MF plus delta MC. And then when you're doing the compression, the final compression, you only have delta MC. And you can actually plug in the values of these particular liquids, because remember, you could also try to calculate the work for this machine cycle by using steady state flow process, first law of thermodynamics for steady state flow processes at the inlet and at the outlet. So you can use that. Remember the equation for steady state flow process, we said was the enthalpy. Then we have dc squared over 2 plus gdz is equals to dq minus plus dw plus or minus dw. And we said that was kinetic energy, that was potential energy. So one of the assumptions which, in the event that you want to deal with the piston, remember, we have our piston, we have our cylinder wall, and we have talked about those other things there. The other one, remember, you have your inlet, valve, outlet, valve, inlet, outlet valve. Then, of course, you have your spark plug there. So you can use that equation at the inlet and at the outlet. And you take, when you're talking about that particular equation using the steady state flow process expression, you'll remember that the flow in that system, in this particular system, is very small. So you can ignore that. You can say it's 0. And of course, there's no change in the datum level. So we can assume the potential energy is 0. So that dH is now dq plus dw. dq plus dw. I don't put a lot of emphasis on plus or minus, because it depends on whether your notation for work done by the system or on the system and so forth, or work done on the system or work done by the system. You can choose work done on the system as positive. You can choose work done by the system as negative. Whichever notation one uses is fine. It's fine. It's fine. In my books, I use the notation minus W to mean work done by the system. So we have these particular expressions there. We have that particular expression there, that is dH equal to dW. But for the polytropic process which we are looking at, there's a diabatic expansion, so we can assume that is 0, so that basically dH is dW. dH is dW. So you'll have to figure out your state points and work with that particular system. Now, what you are saying in a nutshell, therefore, when you are compressing here, you have the delta MF will have exited the system. At this point here, where you are compressing delta MC, both the inlet valve and the outlet valve are closed. They are closed. So basically, these fluids they just move in the process of expansion, compression. One like the one which is in the clearance volume, that fluid there does no work and no work is done on it. It is really inconsequential. Does no work and no work is done on it. It only affects the engine in terms of the capacity, affecting the capacity of the engine. So I think up to that particular point, you can always use also these masses, if you so wish, by realizing some very simple and important element, and that you can now replace these expressions for volumes using the masses by just realizing that volume we talked about was specific volume. Always remember that, and that is meters cubed per kilogram. And so if you multiply by, for example, delta MF times the specific volume, then what you get are the volumes. That would be the mass. This is a mass times cubed over kilogram, which is mass. So the mass you go, so what you get are the volumes. And so when you get those volumes, based on these expressions, compute the volumes at the various state points, then you can put in those expressions for those volumes which you are seeing here, which were corresponding to the state points in terms of the masses involved, masses of fluid involved. So where you have both the mass for the fluid plus that of the clearance volume, you use it so. Where you have only the mass of the fluid, where you have only the mass of the clearance volume, like you said, when you're now compressing it from 4 to 1, you only have the clearance volume liquid. So let's stop at that point. We are continuing with our thermodynamic lectures.